Hey. Yeah, thanks everyone. I quite like this event. Quite different from the appetite of other events, right? Everyone's talking about researches, papers, and which is cool. Yeah, this is our paper actually we wrote about 2 years ago when we started up the company. At that time, everyone's still at Oxford. And then now everyone's everywhere else, right? So it's a paper that we co-host with our researchers in FLock, our founders, and William from Imperial and Eric Xin from CMU. I think if you research AI, you know Eric, right? So yeah, so we just recently have this published on arguably one of the emerging AI top journals called Transactions on AI, which you can see here. And what we are trying to talk about is the mechanism that we're using to build machine learning, decentralized machine learning, together with blockchain to solve a lot of issues. For example, this defending against poisoning attacks. So that's why our company is called FLock, Federated Learning Blockchain. FLock, it's a pun, yeah. So a little bit about background about what is federated learning. It's a term in AI, emerging term in AI. It means that you have your compute locally. I think some of the scholars talked about this earlier, right? So your data is actually locally in your own place, like client 1, client 2, client 3. Nothing is linked to any third party. What you do is you have your local model downloaded to your local clients and then train on it. And the updates of the model, because your model will get updated, the update of the model will be sent back to the central model to do aggregation. Then you have a better model without needing to take any data from their end clients. So that's a way that you can actually work in very, very sensitive areas like healthcare, finance, that they don't want to take their data out of their boundary, right? But we can still train a model in a collaborative way because that's important. That's a very important thing to have for machine learning models, to have a larger data set to make sure the model can converge in a beautiful way. So that's, a little bit about federated learning. So what the problem that we are targeting in this, Oh, it's updated, yes. Well, the problem that we are targeting in this paper is about the poisoning attack in federated learning. So the poisoning, what's poisoning attack? Means that, for example, if in one of those nodes, in one of those trainers, right, one of them actually playing evil. They just want to send some random data, some random results to the server aggregator. Then what they can do is, yes, this is a federated learning training. Then I'm just sending some random data back to the server because maybe I don't care about the result. I don't worry about how the result can be. I am just here to play evil. So this is the kind of problem that we are setting, that we are trying to resolve. But also in traditional federated learning, there are many, there are many areas of problems that we're trying to tackle. This is one of them. So in order to resolve this, there are several solutions that we have now. For example, ZK, everyone mentioned it before, right? Yes, you can generate ZK proof to say, oh, this is the data, this is the model that I trained on my data. It is the thing. But then still, the computation efficiency of ZK is a thing, right? We have ZK-ML, we have ZK-ML. So it's not necessary, if every epoch of my machine learning training, I have to do a zero knowledge proof, then it takes ages. But for example, if it comes to more smooth way, for example, our solution, then we don't necessarily have to use this time-consuming technology in every steps of our training. So that's what we propose. Like it's about 2 years ago. So it's called the FLock incentive mechanism. What we do is actually to reward the good behaviors of those users and also to penalize those who are operating maliciously. It sounds very simple, right? But the world is just like this. Some simple rules can actually do a very good result in complex systems. So its migration basically is about this reward and slash in POS blockchain system. I can explain it easier with a with a photo. So what we do is we actually, in every training, just like a federal learning training, right? A group of nodes are training their local data. What we do is we actually randomly take a bunch of them. We call them proposers, who are actually those training the model in this epoch, in this round. And randomly another group of people, we call them voters. Those are the ones to vote on the results. For example, in machine learning, very obviously, we can focus on an accuracy rate, right? Because rewards is all you need. Just focus on the accuracy rate, and then if the model didn't really get the accuracy up, then you'll vote them down. If it does, then vote them up, right? So basically, that's how the peer-to-peer voting and the reward slashing system works in our proposal. So we can simulate, for example, in this photo. So we have a group of proposers, we have a group of voters. If, for example, if there's no bad guys in this whole training, then on the first row, in our participant selection, they'll be selected into proposers and voters. Then in local training, every of the proposers will train their model locally and get the results to the block. So basically, to have the block to verify, okay, this is the training that we're doing. And then next step, doing global voting. Everyone see the block, see the updates of the model. Then we go and check if the model is actually getting better as I'm voting, right? And then next stage, if everything's okay, all good, then we finalize. We give rewards to everyone who are contributing to the model. Someone who give positive increments, someone who also evaluated it well. And then that's it, right? But in other case, in the next row, if there are malicious clients joining the training, those red ones, right? If you see them, yes, they can be grouped in either in proposers or in voters. And yes, they'll do the training. They'll still do the training. They'll get the updates. They'll give it up to the block. And the voters will check the block and then give their votes. So in this whole process, if everyone else, majority of the others, simple majority of the others are voting up and you're voting down, then you will be kind of like slashed out. Similarly, if you're training this one is not giving the model a good improvement, then we will also vote them down or slash them out, right? Not completely, but fractionally. So eventually, these guys wouldn't get a reward, and then the whole status of the model will revert back to what they were before. And yeah, that's basically the whole mechanism that we proposed. In pseudocode it's like this. You can check in details in our paper. So yes, this is a mechanism that we proposed. Then we are trying to do some empirical researches to make sure it works, right? So yeah, we can propose things, but we need to make sure it's solid. So this is 2 years ago, so we are still using Kaggle, low-end default prediction type of data sets. But nowadays, we are already running on large language models, and it's super cool. I'll get to this later. So so we implement on PyTorch and a Tesla T4 NVIDIA card, and we're setting baselines. For example, 10% of the clients are randomly selected to perform, and then also we use a simple federated learning average on the blockchain. Right. So results easily. First thing, of course, if we slash the bad behaviors like very hardly, like everyone have 64 token in the first time and then 32 was slashed, right? We will see that the decreasing line will be very, 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 very steep because, of course, those bad guys are slashed out immediately. And also, but in this case, if we have more and more, this is for the malicious client numbers. So if the numbers are even higher, we can see the distribution of good guys and bad guys is getting the result that we wanted. And also the distribution of malicious proposers, if they are doing bad, right? So if we slash them hardly, yes, it will decrease. And if there are more and more malicious proposers, we can still have the bad guys being eliminated eventually. But also there's the thing. So yes, so survival time for malicious proposals, of course, if you slash them hardly, they will be removed eventually. But also that means you will kind of like hurt the honest guys, because every time you randomly select a group of them and then you slash, right? So sometimes you might hurt some good guys. That's why we have to still pick the number very rationally, maybe in the between, not just slash them hardly, maybe just 8 tokens each time to make sure that we have some time to gain back the reward, even if we have some error killing in the beginning. So this is the result that we compare. Several roles. The very bottom one, so Oracle, is basically if you train it in your own machine, in one single machine, in one single data set, that's how it looks like, right? 97% accuracy. The role above is Fed average without malicious clients, meaning that everyone is honest, everyone is real, right? This is like the golden standard for the benchmark. That's 97.5% for accuracy, and then the one above is ours. Basically, it's FLock, FLock training mechanism that we can maintain the accuracy even when the malicious client rate are like 40%. Basically means like almost about half of the guys are bad guys, but we can still make sure that our training accuracy is 95.5. Whereas if we look at the traditional federal learning with malicious clients without any of the FLock technology, you can see that that training accuracy goes all the way down from 90, 80 to 70. It's basically useless, right? So yeah. So this is the paper and also the experiments that we did to try to prove and solidly prove FLock works in a beautiful way. Yeah, and so to conclusion, the paper that the contributions of this paper, basically we proposed a stake-based aggregation mechanism for federated learning with blockchain, or we call it FLock, and also the peer-to-peer voting and reward slashing mechanism to mitigate the poisoning attacks, and also our theoretical and empirical proofs about it. And eventually also important thing that we actually implemented this whole technology into FLock.io if you're interested. So so except for this, so FLock itself is not just like technology that it doesn't work with anything else, right? It's a training framework. We actually work on any of the interesting solutions in the world. Maybe maybe TE, FHE, one day if they can really work in a way, right? Or we actually have our other paper called ZKFL. It's still in a FLock mechanism, but with ZK to do a better data authentication. And what's more, these are all our papers. So maybe one day, as Dr. Kathy mentioned before, OPML, right? Maybe OPML FLock can also do something. So yeah, these are areas. So I like to. We like to propose those framework type of training mechanisms that can work with many of the technologies. And these are our other papers. One of them in New RIPS in 2022, and one in TAI, and one still publishing soon. So, and there's more to come. So if you're interested in us in any way, feel free to scan the QR code and follow all our socials and updates about us. So this is a paper 2 years ago. So it's still talking about low-end cargo data, right? And still talking about some regression models. So now, 2 years later, we already have capacity to build on decentralized large language models, and to train on real use cases. So we were launching our decentralized training platform next month. So yeah. So feel free to reach out if you are interested in, for example, if you do Kaggle Hugging Face in your Web 2 life and trying to do something in Web 3, this is a great place for you to play with. And also if you have a lot of graphic cards, you don't know how to use it, run with FLock. Thank you.